So in order to understand 17, you had to take some information from number 11. So in number 11, if you went back and figured it out, we figured out that the spring constant of this thing was, of the slingshot, was 1183.3 newtons per meter. And in part B, we figured out the velocity of the rock as it left the slingshot. You don't actually need that for 17. Does anybody want me to go through 11? I feel like, well, does anybody want me to go through 11? Okay, cool. So let's then run through number 17. All right, so it says, take a look at number 11 above. It says, how much work was done in stretching the slingshot? So all of number 17 is just about the slingshot being stretched and unstretched. Okay, so we actually don't even need to worry about gravitational potential energy at all in this problem, right? Does that make sense? I mean, I guess if you wanted to, you could use the GPE from number 11. It turns out to be 220.5. And then you just keep adding it in, and it ends up subtracting out again at the end. All right? So here is the deal. So, slingshot. All right, so there are a few points that I care about. So what we figured out is that, well, no. Okay, so I guess there's 2 points we care about. So right here, this is before he stretches it. All right, so before he stretches the rubber band, well, we can call whatever height it's at 0, and therefore the GPE is 0. Everybody okay with that? The velocity is 0. Velocity is 0, which means that the kinetic energy is 0. And we haven't stretched it yet, which means that our elastic potential energy is 0, right? And therefore, our total energy right now is 0. Everybody okay with that? Okay. Then, Roy stretches this thing. He pulls it way back until it gets to this point here. So at that point, after he stretches it, well, the height is still 0 because he hasn't moved it up or down at all, which means the GPE is still 0. He's holding it at rest, right? So the velocity is 0, which means the KE is 0. The biggest difference is that now we've stretched it, right? So now there's elastic potential energy, right? Follow? Mm-hmm. All right, so the problem tells us that he pulls it back 60 centimeters. So our x is negative 0.6. So if you find the EPE by using that as x and the k from number 11, the EPE ends up being, I think it's 213 joules. Questions with that, you guys? All right, and so then that means that my total energy is 213, right? So, any questions with what I just did there? Good? All right, so A says how much work was done. Well, work is done as he stretches it. It's the change in total energy. So it's TE final minus TE initial. So you get 213 joules, and there's your answer. That's the work that Roy did. Any problems with that? You guys are a little zombier. That's not a word. Yeah, Alex.
I thought that potential energy was conservative force.
You're right. Well, the rubber band is a conservative force, so it doesn't do work. But how did the rubber band get stretched? Right there. I'm a non-conservative force. Okay, so the idea is before he stretches it, there's no energy. He does 213 joules of work to stretch it. So now it's got 213 joules of elastic potential energy. Now when I let it go, now it's got kinetic energy. Where did that kinetic energy come from? From the elastic. So the fact that the rubber band pulled itself forward is a conservative force, and it didn't change the total energy.
I just thought, when it said slingshot, I didn't know
You good?
Yep.
So that was, number 11 is about the firing of the slingshot. Number 17 is about this part of it. Good, you guys? All right, so any problems with 17a? Okay, so here's the main reason I wanted to go over 17. Part B. It says, all right, let's, instead of doing TE final minus TE initial, let's do force times displacement to find the work, okay, and see what we get. All right, so 17b. So the idea is the work that Roy does in stretching the rubber band should theoretically equal the force that Roy exerts times the displacement, right? We already know the displacement that he pulls this thing back is negative 0.6 meters. So if we can figure out how much force he needs to stretch it, then we're done, right? Okay? So it's a spring, though, right? So let's see. The force of the spring is negative kx, right? Follow? So that's negative 1183.3 newtons per meter times the distance that it stretched at that point, which is negative 0.6 meters. So you get 1183 newtons per meter. No, sorry, just newtons. Holy moly, what the hell am I doing? Let's try that again. When you multiply this out, it gives you 710. Sorry, newtons. Cool? All right, so what that represents is when Roy is stretching it, that's telling us that the spring is pulling his hand forward with 710 newtons. So how much force is he exerting backwards? 710 newtons, right? So that means that the force of Roy must be negative 710 newtons, right? Good? Lauren, you're making a squinchy, what's he doing face? So which way is the spring pulling my right hand?
This way.
Yeah, and which way is my hand pulling? Cool? Everybody good? All right. Let's plug in our numbers. So here's my displacement. Here's my force. So plug in the numbers. So the force of Roy is negative 710 newtons. He did that force over a distance of negative 0.6 meters. Multiply this, and it gives you, I think it's 300 and something something. That's not at all right. Oh, it's 426. It's totally 426 joules. Cool? Question?
No, I think my desk was.
Okay. Yeah, Joey?
Can you scroll up? Because I think I have questions.
Okay. Is that too small?
No, it's fine. Okay, so like if the displacement is negative, then why is PPE not negative?
Because it's 1/2 kx squared. So that x is negative, but when you square it, you get a positive.
Okay.
Cool?
Yep.
Okay, so there's a problem here. So we just found the work that Roy did 2 different ways. And ordinarily, at this point, I would say, why are we happy? And the answer would be because they're the same. So now I'm going to say, why are we unhappy? They're not the same. We just calculated the work 2 different ways and got 2 different answers. They should be the same, right? Like, physics should agree with itself. So when I did TE final minus TE initial, I got 213. When I did force times distance, I got twice as much, which makes me nervous. All right, but there's a reason why. Anybody have an idea why? Sure, we got it.
When you're pulling the rubber band back, the force at which you're pulling it is not constant the whole way through.
Yeah. Yeah, why is that true? There's something specific about like rubber bands and springs that makes that true. Do you remember? Can you help out there?
Is it like the more you stretch them, like the closer, like the
The closer it gets to like being able to stretch its maximum, it's harder to force. You have to exert different forces.
Yeah, and actually, after I asked that question, I sort of thought, actually, I'm not sure what answer I was looking for there. But it's this, right? The force that you exert to stretch a spring is not constant. The more you stretch it, the more force it takes, right? Okay? So, there's no way you remember this because it was weeks and weeks ago, but when I gave you guys this equation initially, like weeks and weeks ago, I told you that you could use that equation to calculate work as long as your force was constant. All right, and usually it is, right? Like Roy pushes with 300 newtons, or friction is constant, right? A spring is the one of the weird exceptions where the force the spring exerts is not constant, okay? The other type of force that we talked about that's not constant is air resistance. Problem 13 had the guy jumping out of the airplane, okay? So here's the moral of the story. If I just lost you and you're like, well, I have no idea what's going on, here's all you need to know. If your force is changing, you can't use this to find the work. You have to use this. Cool? So, when is the force changing? Well, really, we've only learned about two forces that change. Springs, or rubber bands, and air resistance. Cool? I don't remember if I put one of those on the test, but I'm calling attention to it as a just in case. Cool? Yeah, LaShawn.
I'm just confused about the signs, because like sometimes I get that mixed up.
I gotcha.
Like if I were to like mess up on the test, how bad?
It depends on the context of the problem. I guess what I would say is this. So, in terms of energy, what does it mean to have, for example, a negative work? Okay, that's in terms of the forces. Okay, so yeah, so if the force is one way and the motion is the other way, then the work is negative. Okay, so that's one thing you should know for sure. Friction will almost always be negative work, right? Right, because you slide one way, friction opposes it. So friction usually is negative work. But what does it mean to have negative work? In terms of energy, what does it mean to have negative work, you guys? This is super important. Nate, what do you got? That you're losing energy. Exactly. Do you guys agree that friction makes stuff lose energy?
Yeah.
Okay. So I guess I would just be mindful of that, LaShawn. Worst case scenario, you forget a negative sign, and depending on how bad it snowballs, it might be a couple points. If you do everything else right, but just miss that negative sign, worst case, it's 2 points. Cool? The only problem is, can you ever have negative kinetic energy, you guys? If you get a negative kinetic energy, odds are that was your mistake, is that you missed a negative sign somewhere else. So go find it. Okay? Cool? Does that help any? Ish? Okay. All right. So are we good with 17b? Moral of the story. Again, this guy. Only if the force is constant. Cool? All right. Last but not least, 17c says, find the power the slingshot is generating when it's halfway unstretched. That is, after Roy has released it, and when the slingshot is still stretched 30 centimeters. Okay? So, in other words, it's this. So, here's the slingshot again. Oops. That was dumb. Oh, look out. Sorry, I almost killed you. Are you okay? Okay. Whew. All right, so, the idea is we just figured out that when the slingshot is here, that the elastic potential energy is 213 joules, right? Okay? So the question wants to know, when the rock gets to here, halfway between the red dot and this green X, it wants to know how much power is being generated. So P equals what at that blue dot? Okay? So here are the things I know. I know it's still stretched, 0.3 meters, 0.3 meters. So, what kind of power are we looking for here, you guys? Instantaneous or average? Instantaneous, right? Because it's asking for the power at that instant right there. Okay? And the only way to find instantaneous power is to find force and velocity and multiply them. Force times velocity. That's it. I mean, like, that's the only way to do it. Okay? So, unfortunately, this is it's a two-step problem for us. We got to find the force, we got to find the velocity. Okay? Which one of those two things is pretty easy to find? Velocity? Okay, I think the other one's easier, but that's cool. We can find the velocity. All right, so to find this velocity, let's think about what we know. We know at that blue dot, we know that our x is 0.3 meters. What should I do with that? Why do we care about x? The distance you use to find your EPE, right? So our x is 0.3 meters, so I can find my elastic potential energy just by doing 1/2 kx squared. Follow? Okay, so if you do that, it gives you 53.25 joules. So right here, that's how much elastic potential energy we've got. So now what? I'm kind of stuck. We're trying to find the velocity, right? The only way I can find the velocity is to find the kinetic energy. But since I don't know the velocity, I don't know the kinetic energy, I'm stuck. So I should ask myself, is the total energy changing? What do I know about the total energy? Well, over here, the total energy was 213, right? So, Joey, I'm going to pick on you for a second. Or maybe it wasn't Joey. No, I guess it was Alex. It was Alex. Sorry. Alex. Should the total energy change between here and here?
Shouldn't change, no.
How come?
It's a conservative force.
Because it's a conservative force. Do you understand why this is now different than it was before when we were stretching it? Everybody good? Okay. So that means that my total energy over here has got to still be 213. So now I can subtract to find my KE and find the velocity, right? So 213 minus 53.25 gives you 159.75, which I can now use to find the velocity. So times 2 divided by mass, square root it, gives you 20.6 meters a second. So that's the velocity when it's halfway unstretched. What's the other thing I got to figure out? Force. Force, right? Because P equals FV cosine theta. So I've already got my V. So I got to find my force. Anybody see an easy way to find the force? You're warm. Name the force, you guys. What force? We're looking for the power generated by what? The stretched rubber band. So how do you find the force from a rubber band or spring? Negative kx. Yeah, you just do F equals kx. Well, negative kx, I guess. I would say don't get too worked up about that. So point for me, you guys. Which way is the rubber band pushing the rock? Isn't it pushing it that way, right? It's like flinging it forward, right? LaJohn, you see that? Everybody good? Okay. And the velocity's that way, right? So our angle is going to be 0, right? Cool? All right, so let's see. So our K is 1183.3. The X is negative 0.3 because we've pulled it back that far. So multiply this out, and it gives you not enough room on the board to write it. Is it 256.2.3 times 1183.3333333? Nope, 355. It's way off. So there's the force of the spring. So now you just do force times velocity, and you get the power. Oh, I'm sorry. Remember the time I broke your ankle? Terrible. Just now? I stepped on your foot? Never mind. I'm sorry. I'll leave you alone. I'm going to go over here now. All right. Questions on that? That was tough. Here's the takeaway from that. I think if I'd put this on a test, I probably would have broken it up into more steps. Find the velocity when it's halfway unstretched. How much force is applied there? What's instantaneous? Okay. You ought to be able to understand the individual parts of it. That was a lot, though, for one problem. Questions? Any problems with whatever number this was, 17? Going once? Twice? Sold. Okay, so